All right, time to do some practice, and we're actually going to do it a little bit different this time, and we're going to focus on one very particular type of problem, namely implicit differentiation. And it's a really simple idea, and so if you can just remember the following, it says, hey, I may not know exactly what the function is, but I can pretend. And if we use that mindset, the problem doesn't become so bad. Of course, you got to practice it, which means we got to do problems. So do problems. If you're following along with the video, make use of the pause button. See a problem? Pause. Try it out. See how you do. And when you're ready, you can unpause. I can either help or we can compare answers. Either way, together we'll learn something. Well, let's begin. So, our first problem. Find partial z, partial x, and partial z, partial y, given you have this relationship. Z plus e to the xz plus sine of xy plus y cubed equals 17. Okay, so the thing is, this is implicit in the following sense. There's no way we can get z by itself. You see, z is shown up in two places. There's no way to reduce it down to a single z using simple tools. But nevertheless, we can still ask and answer questions about how things are changing. Because it's true, if you specify an x and a y, it's not that there's arbitrarily many z that work. No. Only one, two, sometimes. And so z still depends on x and y. So remember, our basic mindset here is the following. And we'll draw this picture a lot. We'll say, okay, we're going to think z is a function of x and y. All right, great. And once we have that, pretty much everything else just follows. What do? Well, start by taking the derivative with respect to x. So I'm denoting it as partial x. The reason I'm using the partial symbol is because we're thinking this as having two things that can vary, x and y. So when I have two things that can vary, I use the partial symbol, not the symbol d. So everywhere where there's an x, I have to remember to take a derivative. Now, where is there an x? Let's be really explicit here at the start so we can make sure we don't make a mistake. Well, you're probably saying, easy. There and there, right? 2. But there's more. Remember our thought. Z is a function of x and y. So every place where there is a z is also an x. Because when we think, now we would never write this down in practice, but since we're doing it with friends, we'll do it one time just so we can get our mindset going. What we're really saying is it's z of x comma y plus e to the x times z of x comma y plus sine of x times y plus y cubed equals 17. So the z does have an x involved. All right, so now we know. So we go through term by term. And what do we have? Well, the derivative of z with respect to x is the derivative of z with respect to x. Exactly. It's something. We know z depends on x, we just don't know exactly how, so we call it partial z partial x. Here, we use the chain rule. So the derivative of the outside is the exponential function. Plug the inside in, times the derivative of the inside. Product rule. Derivative of x with respect to x is 1, so that's a z, plus the derivative of, so it's 1 times z plus x times the derivative of z with respect to x, partial z, partial x. Good. Go to the next term. Derivative of sine of xy. Well, chain rule. Derivative of sine is cosine. So the inside stays the same times the derivative of the inside. The derivative of x times y with respect to x is y, because y is acting like a constant. Derivative of y cubed, 0. Remember, in this setting here, x and y are the variables. In other words, they're independent. So it doesn't matter what's happening to x, y can do its own thing. That's why we talk about the derivative of y, it's 0 here. In some sense, if you go along, you'll hear words like dependent variable, independent variable. So we're thinking of z would be called our dependent variable because it depends on other things, x and y. Whereas x and y are independent because they don't depend on what other things do. So anyways, okay, are we done? No. What do we have to do? Well, we have to take the derivative of both sides. So we also have to take the derivative of 17 with respect to x, which is 0. Now, the moment of truth. If we do our math right, then it will always be the case that we can put all the terms with a partial z partial x together and all the terms without a partial z partial x together. In fact, we'll just move everything and split it to two sides. So what has a partial z partial x? Well, we see that there's a one of them there, and then, remember that this will go through, there will be an x e to the xz. Now, what doesn't? We'll move it across. Well, this first term that distributes, so I have minus z e to the xz, and here minus, I like to put the y first, looks a little bit nicer, y cosine xy. And now, we've almost got partial z partial x. We just have this other term here. Now, this is one of the things you have to be careful about with notation, because it kind of looks like you're plugging something in, but these are the parentheses of multiplication, not the parentheses of evaluation. So we're going to divide here, and we come to the conclusion that, aha, partial z partial x is minus z to the e to the xz minus y cosine of xy divided by 1 plus x e to the xz. Good. Halfway. Because remember, we had to find two things. So far, we found the partial z partial x, which means time to switch gears. Partial z partial y. So for that, what are we going to do? Well, we're going to take the derivative with respect to y. So, how many places does y show up? Well, we can mark them, right? There's a y there, and there's a y there. But, of course, it also is inside of the z. So there's a total of 4. So we go through and take the derivative with respect to y. Derivative of z with respect to y is the derivative of z with respect to y. Okay, well, that's not so bad. Cool. Go to the next term, chain rule. That'll be e to the xz times the derivative of x times z with respect to y. Well, x as a constant, so it'll be an x times the derivative of z with respect to y, which is the derivative of z with respect to y. Okay, how about sine of xy? Well, that'll be cosine of xy, because doing chain rule, derivative of xy with respect to y is x. Great. Derivative of y cubed with respect to y, 3y squared. Take the derivative of the other side. Derivative of 17, still 0. Doesn't matter with respect to x or with respect to y. 17 is 17. So, pull out the partial z partial y. It's actually a little bit easier here, isn't it? So we get 1 plus x e to the xz. Move the other terms across. So we'll have minus x cosine of xy minus 3y squared. And therefore, we come to the conclusion, after we divide, partial z partial y is minus x cosine of xy minus 3y squared. Divide that by 1 plus x e to the xz. And we're done. That's it. We're finished. Ha! That wasn't so bad. Just remember, what do we need to think about? Well, we think about the function that we can't write. Well, we say like, we pretend like we could. And then we proceed forward. And then life is good. All right, well, let's try another one. So this one, very similar. where we're asked to find partial u partial s and partial u partial t, given that e to the s times u plus 3u cosine t minus st equals 1. Now, the really only different thing here is the names. And I want to pause and say we shouldn't be caught up on names. And I know we get so used to it. It's like, okay, x and y and z. And I'm like, we have to use x, y, and z. It's like, And sometimes when we see new symbols, we're like, these are different symbols. It won't work, But it will work. That's the wonderful thing. It's the same process. Nothing's really changed. And so, what do we have? Well, we can identify our variables. So there's 3 of them. There's u, s, t. So there's u, s, and t. Now, which ones depend on which ones? Well, if you look at it, we're asking, how does u change with respect to s? And how does u change with respect to t? So that means that the way we think about it is we say, okay, we're going to think about this as u really is a function of s and t. So every time we see u in our equation, we'll say, secretly, it's some function of s and t. We just don't know what it is. And now we're ready to go. So to find partial u partial s, well, that says we better look at the derivative with respect to s. So we come here and we say, well, we're going to need to use the product rule because u also has an s in it. So derivative of the outside. Inside stays the same. Product rule. Derivative of s with respect to s is 1 times u plus s times the derivative of u with respect to s, which is the derivative of u with respect to s. See, that wasn't so bad. All right. Now here, well, cosine t is acting like a constant, as is the 3. So the only place where an s is the u. So what do we have? Well, we have 3 cosine t and partial u partial s. In other words, the derivative of u with respect to s. Derivative of s times t with respect to s will be t. Remember, t is acting like a constant. Make sure you take the derivative of the other side, and remember, derivatives of constants are 0. It's really tempting to forget that sometimes. So what will happen if you do it right is you'll always be able to factor out a partial u partial s times some stuff. If you can't do that, you've made a mistake somewhere. Go back and check your work. So we're going to have s e to the su there, and then here, 3 cosine t. On the other side, we'll move that across. That'll become a positive t, and then we have this other term, which I'll write as minus u e to the s times u. All right, which tells us partial u partial s is t minus u e to the s times u. Divide that by s times e to the s times u plus 3 cosine t. Okay, good. Well, that's it. See, that is partial u partial s in the following sense. If you give us any point, stu, so in other words, a set of values which satisfies this relationship, then if you plug in the s and the t and the u, that will tell you that on that surface, how is u changing with respect to s. All right, well, let's finish the problem, because we've already finished the partial u partial s, so now we have to do partial u partial t. So that means we're taking the derivative with respect to t. In the first place, the only place where the t shows up is inside of the u. So it's e to the s times u, and then s is a constant, so we're going to have s, and it's going to be partial u partial t. Here we're going to have a product rule, because t is showing up inside of the u, and it also shows up in the t. So 3, derivative of the first, well, the derivative of u with respect to t is partial u, partial t, and then we have cosine t, and then we have 3u times the derivative of cosine. Well, that's the negative sign, so we're going to end up with a negative sine t, and then come to the last term, derivative of s times t with respect to t is s, and take the derivative of the other side is 0. So we see, okay, we can factor out the partial u, partial t. We'll have s e to the s times u, then plus 3 cosine t, and that's going to be equal to s plus 3u sine of t. So, come to the conclusion, partial u, partial t is s plus 3u sine t. Divide that by s e to the s times u plus 3 cosine t. And good, and we're done. Now, you might notice, and probably it's not very surprising, but hey, you're like, wait, the denominators are the same. Is that a coincidence? No, they should be the same. And indeed, if you work through these types of problems, you'll see that the denominators turn out to always consistently be the same. So that's another way to sort of check yourself. It's like, hey, my denominators aren't matching. Something's happened. And, okay, all right, well, let's go on. More problems, yes? Okay. Well, the first derivative is so nice. Let's do it twice. So, given the implicit relationship, z plus e to the z equals x times y, we want to find partial squared z, partial x, partial y, only in terms of z. Okay, cool. So we're going to go for the second derivative. We're going to go and take not one, but two derivatives. Woohoo! Nice! All right. Well, how are we going to do it? Well, we're going to do it, as they say, very carefully, because it's easy for us to get lost, and we don't want to do that. So let's think about what we have. Of course, we have in the back of our minds, we say, well, look, we know z is going to depend on x and y, because what we're asking here is, if we look at this expression, how does z change as we're changing x and y? All right, great, no problem. So let's talk about partial derivatives. Now, we need to take two of them, right? One with respect to x and one with respect to y. And one thing to keep in mind is it doesn't matter which order we take it. So we're going to say, look, just take it in whichever order is convenient. So let's think about our possibilities. So one possibility, suppose we take our derivative with respect to x. Now, just for notation's sake, because we're going to go along here, I'm going to switch from using partial symbols to using subscript notation to denote derivatives. But just remember, it's still the same thing, it's just different notation. So when we take derivative with respect to z, we'll have z sub x plus, okay, so that's the derivative of z with respect to x, plus then we have the derivative of e to z, well that's e to the z, times the derivative of z with respect to x, which is z sub x, equals, on the other side, well, take the derivative of that with respect to y, with respect to x, and we get y. Okay, good. Now, what else? Well, if we wanted to, we could have taken the derivative with respect to y. Now, I'm starting with the original equation here. And we can say, look, z sub y plus e to the z, z sub y equals x. All right. That's very similar. There's a lot of symmetry going on here. Now, there's kind of two schools of thought. One school of thought says, well, let's solve for these partial derivatives. So, for instance, z sub x, it's not hard to do. You factor it out and divide, and you get that. You get y over 1 plus e to the z. Or if you did that down here, you'd say z sub y would equal x over 1 plus e to the z. Now, how do we get zxy, you ask? Well, let's say what it's not. Z sub xy is not the same as z sub x times z sub y. So, as a word of warning, just this is not zx, zy. Okay? I mean, it feels like there should be something like that, but that is not how partial derivatives work. What we have to do is we have to take a derivative of a derivative. And I said a little bit ago that there were sort of two schools of thought. One school of thought is, well, let's solve for zx and zy, and then let's take a derivative. And so, for example, let's take the derivative of both sides with respect to y. What rule will you need? You'll need a quotient rule, right? Because you have a division, and there's y's both upstairs and downstairs. And it's just like, oh, do we really want to do a quotient rule? And the answer is no, we don't. So, okay, so we're not going to do a quotient rule. And you're probably saying, but how? So that's where we come back and say, the other thing to do is just to say, look, let's start with one of these expressions. Doesn't matter which one. I'll start with this expression and the whole thing. And now we're going to take the derivative of this with respect to y. So I'm going to take the derivative of both sides with respect to y. Now, before we go too far down this path, I want to be careful here. We were thinking to ourselves, hey, z is a function of x and y. What's true about z sub x? So as we continue our thoughts, what can we say about z sub x? What will z sub x be a function of? Do you know? It will be a function which depends on x and y. So in other words, if I start out with a function which depends on two variables and I take a partial derivative, I still have a function which depends on two variables. So I still have the two variables in play. So let's keep that in mind as we go through here. So where does y show up? Well, it shows up in 1, 2, because it shows up inside the z, 3, the z sub x, and 4. Wow, lots of y's. So, working our way through it. Well, the derivative of z sub x with respect to y, well, that's z x y. Great. Just what we want. Derivative of here, e to the z times z sub x, product rule. Well, the derivative of e to the z, well, that's e to the z, and then times zy. So that's the derivative of the first times the second plus the first. I'll just use parentheses to really separate these. Times the derivative of the second. Derivative of z sub x with respect to y is zxy. And that, of course, equals 1. Well, now we're actually in great shape. What can we do? We can say, look, we'll gather these derivatives. Now, these derivatives here, that's actually what we're after. That's the second mixed partial derivative. Derivative of z with respect to x and respect to y. So, in essence, it's what we want. So we get zxy. Well, let's factor it out. There's a 1 plus e to the z is equal to 1 minus e to the z. Say 1 minus, and then e to the z times zx times zy. Well, we're almost done. That becomes zxy. What we're after is 1 minus e to the z times z sub x times z sub y, all over 1 plus e to the z. Okay, now, we're not actually done. What's wrong? Well, the thing that's wrong is we have these pieces here, zx, zy. We don't want those in our answer. We want to replace them. And now we say, but wait, we know zx and we know zy. So we'll replace them, and then we'll be good to go. So what do they become. Okay, so this is equal to 1 minus e to the z, and then zx y over 1 plus e to the z, and zy x over 1 plus e to the z, all over there, 1 plus e to the z. Great, great, wonderful. Well, now what? Well, we can clean it up. If we multiply top and bottom by 1 plus e to the z squared, because there's a 1 plus e to the z and another 1 plus e to the z, that gets rid of our 1 plus e to the z's in our fractions upstairs. In other words, it gets rid of fractions within fractions. We can come to the conclusion that, hey, 1 plus e to the z quantity squared minus e to the z times xy over 1 plus e to the z cubed, that is our z sub xy. Except it's not. What's wrong? Okay, what is wrong? Well, go back to the original problem. It says, hey, only in terms of z. Now, it's kind of rare that you can do this. So this is not like, oh, we'll always be able to do this. It's kind of a little bit of a special function. Now, what's our challenge? Our challenge is the x times y. That's not in terms of the z. Those are other variables. Is there anything we can do with x times y? And what is it? Well, we know what x times y is. X times y is z plus e to the z. Aha! We can make progress. Okay, so let's clean it up. So first off, let's square the first term. That would be 1 plus 2 e to the z. Then e to the z quantity squared would be e to the 2z. Subtract, we're going to take e to the z times this. Well, e to the z times z, well, that'll be z e to the z. And then e to the z times e to the z will be e to the 2z. All of that over 1 plus e to the z quantity cubed. And we say, aha, beautiful things are happening. The e to the 2z's cancel. And so we have now our final answer. What is this? Well, we have 1 plus, now here, these terms both have e to the z, so I can rewrite that as 2 minus z times e to the z, and divide that by 1 plus e to the z quantity cubed. And that's it. We're done. Aha! Wonderful, wonderful progress. So, good. And of course, it's just a matter of take the partial derivatives, keep track of notation, clean it up, and make sure you know what things are, but also, of course, make sure you know what things are not. Too often people make mistakes like that. No, we don't want to make those mistakes. Well, we don't want to make any mistakes, but we definitely don't want to make silly mistakes. Make interesting mistakes. Life is better that way. All right, I think we have one more problem, which will take this one and kick it up a notch. So let's do that one. So we're going to take the preceding problem and say, let's do it completely symbolically. So instead of doing a special case, we're going to say, suppose we have some function f of x, y, z equals 0. And we want to find partial squared z, partial x, partial y, all in terms of derivatives of f. So when we talk about derivatives of f, we mean partial derivatives. Well, it should be interesting by the time we get done. But if you remember the process of the last problem, you're going to see, oh, we're going to do a lot of the same things. So where are we going to start? Well, we're going to start by taking first the partial derivatives just with respect to x and with respect to y. Now, what do we have? When we look at this expression, we're really thinking to ourselves, okay, we're going to have that z depends on x and y. That's our thought. Z depends on x and y. So if you think about how the variables connect, well, we say, okay, f depends on x, y, and z, which depends on x and y. So here we go. When we take the derivative with respect to x, what will happen? Well, x shows up in two places. So we're going to have f sub x, and that's that route. Plus, then we have an x showing up down there. And the way we do that is we're going to take f sub z, that's the derivative of f with respect to z, times the derivative of z with respect to x. So f z, z, x. This is all shorthand. So another way we could have written this is partial f, partial z, partial z, partial x. And that is going to equal the derivative of the other side with respect to x, which is 0. All right. Partial y, what is that? Well, similar thing. Y shows up in two places. So straight down, f sub y, and then f z, zy. So plus f z, zy equals 0. Now, we're ready for our next round of derivatives. We're not going to solve for anything yet until we need to, and we don't want to introduce fractions if we don't have to. Fractions tend to make things a little bit more complicated. At least that's my experience. And so I'm not that I'm opposed to fractions. I mean, I certainly believe that fractions have a right to exist, but I do think that fractions make things more complicated than they need to be. So let's hold off if we can. Now, one thing to keep in mind is we said, look, our function f, that really is a function of x, y, and z. But the same thing is true for f sub x. It also is a function of x, y, and z, and f sub y. It's also a function of x, y, and z. Put another way, if this is our tree for f, we get the same tree for fx. And for fy. If we wanted to, it doesn't really matter which one we draw, because when we take the partial derivatives, we still have the same variables in play, we still have the same relationships showing up. So it doesn't matter which one we start with. So I'm going to go to, say, the first one, and I'm going to go here and focus on take the derivative with respect to y from this expression. So f sub x, where does y show up? Shows up in two places. So we're going to have the derivative of f sub x with respect to y, which is f x y. And then we're going to have, going down, plus f x z. In other words, I'm taking f sub x, take the derivative with respect to z, times z y. So that's the derivative of f sub x with respect to y. Plus, okay, now we come to f sub z. Well, what is that? Take the derivative. Oh, I forgot to draw it. What is fz? Same thing, right? So we still have our x, y, z, x, y. So I want to look at the derivative of f sub z with respect to y. Well, we're going to get fzy. Right? Fz with respect to y. And then we're going to have fz with respect to z times derivative of z with respect to y. Now, that is the derivative of fz with respect to y. And we're doing a product rule, so that's multiplied by zx. To this, we add the first term, fz, times the derivative of zx with respect to y, which is zxy. And now set that equal to 0. Okay, good, good. Now, good news. What do we have? Well, we have what we're after. We have z, x, y. It's right there. So all we have to do, oh, like it sounds easy. We just have to get that by itself, only in terms of the derivatives with f. Well, how do we actually achieve that? We go through and we clean up is what we're going to do. So, for instance, if we come back here, we can say, look, we have some zy terms showing up, and we have a zx term. We don't want those, because we only want things in terms of derivatives of f. How do we know we only want things in terms of derivatives of f? Because it says, in terms of derivatives of f. That was sort of our big clue. It's our big aha. We see where you're going. So, let's think about that. What is z sub y? Well, z sub y I can solve. So z sub y is minus fy divided by fz. How about zx? Very similar. Zx is minus fx over fz. Great. Perfect. Wonderful. So we can replace all these pieces. So we have in the first piece here, minus fy over fz. And here, we're going to have a minus fy over fz. And there, we're going to have a minus fx over fz. Okay, so we're going to replace all those in. Now we have a bunch of partial derivatives of f and z sub xy, which is what we want. Aha! Cool. So once we clean it up, rearrange, then we're done. Now, we now have some fractions. So let's get rid of the fractions. And the way we're going to get rid of fractions, probably won't surprise you, is we say, let's clean out our denominators. And if you look, there's an fz. Here there'll be an fz and another fz. So if we multiply everything by fz squared, that will do it. So what do we get? If we multiply through by fz squared, well, we're going to get fxy fz squared. Okay. Here, we'll cancel one of the fz's. So we're going to get minus fxz fy fz. All right. So that's the first term, the second term, the third term. Well, we have to be a little bit careful here. So we have fzy times this minus fx over fz. So we're going to get minus fzy. So the minus is coming from the minus there. fzy, there's an fx, and we cancel one of the fz's. But we still have one fz left over. Now, for the next term, we have fz. That cancels with both the fz's. Good. So that's gone. The minus and the minus become a plus. Oh, good. And so what do we have? fz, and then there's an fx, fy. And in the last term, we're going to get fz cubed, zxy, and all that equals 0. Okay, well, we're getting close. So we've cleared out all the denominators. All the denominators now are gone. So the last thing to do, let's move these terms across. And so we can say, hey, fz cubed times zxy is equal to, and then we're moving all these four terms across. So we get minus fxy fz squared plus fxz fy fz plus, and by the way, fzy is the same as fyz. So we'll write it as fyz fxfz minus fzz fxfy. And the last thing for us to do is divide. So we come to the conclusion that zxy, this term right here, which is a shorthand notation for partial squared z, partial x, partial y, is equal to, well, copy it down again, minus fxy times f quantity z squared. So this is take mixed partial derivative of f sub x and take that with respect to y. Here, take the derivative with respect to z and square it, plus fxz fy fz plus fyz fx fz minus fzz fx fy, all divided by fz cubed. That's it. Wow. Amazing. Amazing. Well, probably we should say a couple of things. It shows you how things really ratchet up. You know, when we're talking about implicit differentiation, things get a lot more complicated. Our inability to know how things change make it a little bit harder to work with. So even when we look at the first derivatives, it's like, well, okay, these aren't so bad. How bad could it be if we get to second derivatives? And the answer is, it could get this bad. So it could change quite substantially. I will say I put this on a final exam many, many years ago. And this was back when I was teaching at a different school. It was a community college out in California called UCLA. And I had two very smart TAs for the course. And I know one of them is a professor somewhere. I've lost track of the other one. And neither of them got it. So both the TAs failed to answer this question because they weren't patient. They rushed and they thought, oh, it's just super easy, no problem at all. On the other hand, there were some students, not all, definitely not all, but there were some students in the class who actually got it. So it goes to show you, don't underestimate your abilities. You might think, I'm not as good as those really smart people who've been doing this for years. Sometimes they're overconfident and they don't think about things. It's important. Take your time, be methodical, and think. Thinking is so valuable. Well, that one, that was what a doozy to finish on, and a great place for us to stop with our practice with implicit differentiation. Definitely don't memorize this formula. You'll never need it. All right. See you another time. Bye.